All right, good morning, ladies and gentlemen. Welcome back to another installment of ICP. It is Thursday, March 11th, 2021. And today we're going to be talking about electricity. So without further ado, let's go ahead and get started. So today we are going to be working out of day 20, all right, electricity right here. Please go ahead and open up the electricity guided notes as we go through the PowerPoint. All right, so without further ado, let's go ahead and get started. Okay, so today we're going to be talking about electricity and a little bit about magnetism. So we're going to be talking about static electricity, currents, circuits, and then magnetic fields and a little bit of this other stuff as well, but not too much. So first off, I'd like to ask you guys the question, what is electricity? I do this because a lot of times we take electricity for granted. We know, where it comes from. We know that we use a lot of it throughout the day, but we don't actually think about what is electricity and why are we talking about electricity in chemistry, right? Because it doesn't necessarily make sense. We've just been talking about bonding. We've been talking about the structure of the atom. We've been talking about balancing chemical equations. And now all of a sudden we're talking about electricity. And then one thing I find, if you don't know quite what electricity is, you know what kinds of material allow electricity to flow very easily. And you may know some that don't allow it to pass through very easily. And we're going to be talking about those today. So keep these questions in mind because this is kind of where we're going and what we're going to be talking about today. So a lot of people struggle with that idea of what is actually happening with electricity. How does that actually work? So let's get into it. Well, first off, we need to understand the world is full of electrical charges. And that's why sometimes those charges build up and we can kind of see some kind of discharge of those charges. But everything has charges. And what can happen is as these charges build up, become more positive and more negative, we create a potential energy, right? Potential, we talked about potential and kinetic, the movement for kinetic, and then potential being stored energy. So static electricity is the buildup of stored energy. All right. So static electricity, like I said, is the buildup of an electrical charge on the surface of an object. What's key here is the charge builds up, but it does not flow yet. That electricity is not moving yet. And static electricity, like I said, is a potential energy because it builds up, but it does not move. You guys say, hey, Nick, I've dealt with static electricity before and I get shocked. Well, that's actually not the static electricity. That's what comes after the static electricity builds up. And that is static discharge. So once there is a loss of static electricity due to three possible things, either friction, rubbing things together, you see those shocks, conduction, you touch something and you feel that shock, or induction, if you get close to something and there's so much charge that it jumps from one thing to the other, but not direct contact. So one of these three things is going to cause that static electricity to move, and that is static discharge. That's more of a kinetic energy. So friction, obviously, like you think about, like if you rub a balloon on your head, that builds up the charges, and then you kind of maybe see little shocks, but it also attracts your hair. Again, conduction, if you go and you touch a doorknob or something like that, and you feel that shock from direct touching, that's the static discharge there. And again, if you get close to something and it shocks you, that would be the induction. All right. So electricity moves pretty much wherever it wants, okay? And electricity is really the movement of electrons, okay? That's what electricity is, the movement of electrons from one atom to another. And the key is that it does that wherever it feels like it, unless we give it a place to go. And we're going to see that here in a minute. But we call that movement of electricity or movement of electrons. We call that current. And again, that's movement of electrons from one atom to another. We measure current in amps. So how many amperes of electrical current are we dealing with? And because this is movement, remember this is a form of kinetic energy. Kinetic energy. Okay. So obviously we don't want electricity just traveling wherever it feels like, because then it's going to shock things, it's going to fry things, and it's not going to power the devices that we really need. So the key here is that we're going to control where the electricity flows with a circuit. Okay, we're going to give it a path to follow. So think of a circuit as like a racetrack. It's a closed loop, and those electrons, that electricity, is going to move around and around and around and around and around. And what we use to create a circuit is we use wires. And I want you to think about a wire, because a wire is a good thing to think about to remind yourself what allows electricity to flow and what allows electricity not to flow. So what are really good wires made out of? Well, they're usually made out of one of two things, either copper or aluminum. Copper is better. Copper is very, very, very conductive of electricity, allows it to flow very easily. So we use like really high quality electrical wires are going to have copper in them. Aluminum, if you have ever accidentally messed up a phone charger and maybe you saw some silvery metal, that's aluminum. That's still a pretty good conductor of electricity, but it's not necessarily for the higher, amounts of electricity to flow through. Your phone doesn't need a lot of electricity to charge, so it's fine that it has an aluminum wire instead of a copper wire. So those electrons are going to travel around and around and around. And the key is they cannot travel elsewhere, because what is the wire covered in? Well, the wire is covered in some kind of plastic or rubber. So obviously you can realize that those things are not going to allow electricity to flow through them. So we've already talked a little bit already now about conductors and insulators. Now, there are two different types of currents or ways the electrons can flow. The first is a direct current, DC. All right, DC or direct current is where electrons flow in the same direction around a wire. Think about this as a one-way street. Cars can only travel a single direction down a one-way street, just like a direct current. Those electrons are only going to flow in one direction through that circuit. And that's very important, because the other type of current is alternating current, where they actually move back and forth. They can go in different directions. This is more of like a two-way street, or going forwards and backwards. So they can go in both directions. Can I help you?
Sorry, I'm trying to.
Oh, he's fine. He's going to be how he's going to be. All right, just like there are two different kinds of currents, there are also two different types of circuits. So the first type of circuit that we're going to see is called a series circuit. A series circuit is where all the components could be anything from light bulbs, anything that's using electricity, speakers, a device, a motor, whatever it is using that electricity, that's called the component. So all the components are lined up in one path. What this means is the electrons have to go through all of the components to get back to the starting point. There is one path for that electricity to follow. So the important thing is if for some reason that path gets broken, the entire series is going to turn off. All the components will turn off that are attached to that series circuit. So it's got to go through one component, then the other, and then back to the start. If one of them goes out for some reason, like if one light bulb goes out, they all go out. So the best way I can talk about a series circuit is, they don't make them so much anymore, but they used to make Christmas lights as a series circuit. Think about Christmas lights. They're in a string, and the old ones, if one went out, the entire strand went out. And you had to sit there and go through and replace one light bulb at a time until you figured out which one of those 100 light bulbs was burned out. And then hopefully the thing would turn back on. We still use series circuits in other ways as well. Series circuit is exactly what an alarm system uses. When the door is closed on the alarm system, there's two connectors that are touching, and that allows the current to flow. And then as soon as that door is opened, that circuit is broken, and that triggers the alarm. Okay, so there's reasons that we still use series circuits in everyday life. These can also be like safety shutoffs. So if you're working in like a factory or something like that with lots of machinery, a lot of times they'll have a button that turned off the entire, line. And that is, all of those components being at some point connecting to the same spot, making it a series circuit. You'll see that we can use series circuits and the other type of circuit we're about to talk about oftentimes together, but different uses for the different types of circuits. So here's a picture of the series circuit. Let me pull up my little laser pointer so you guys can see where I'm talking. So electrons have a negative charge. So they're going to come out of the negative side of the battery. This is the active one. And what happens is the electrons will flow through the wire along the path. They will go through the first light bulb, the second light bulb, the third light bulb, then the fourth light bulb, and then back to the battery. And the reason they are moving is because there is a positively charged part in the battery that's attracting the electrons, but there's actually a little trap door. So as the electrons get close to the positive charge, it actually pushes them past it, and then they have to go all the way back around. And that's how a battery works. So there's a positive and negative side. Also a free little lesson. When you're jumping your car battery, which side do you want to connect first? Well, you want to give a place for these electrons to go. So connect the positive side of the battery first, then the negative side. Positive side is usually red, and then the negative side is the black side. But in any case, if something were to happen to one of these light bulbs, let's say the second light bulb blew out, right? It's no longer working. The key here is that the entire set of light bulbs is going to go off, because as these electrons travel around, they might go through the first one. If they don't have a path to get through here, they stop. There's no other route. There's no other way for them to move. So the whole thing shuts off. That's a series circuit. The other type of circuit is a parallel circuit. Parallel circuits have several branching pathways to each of the components. So basically that means that there's multiple pathways for the electrons to flow. So if in this case, if one of the components goes out, just that component or that branch is going to go out. And we'll see what that means in just a moment. Let me take a look at this picture. So here we can see this one is set up very differently because, again, the electrons are going to come out of the negative side, but they have multiple pathways. Electrons can go through this first light bulb and then back. Electrons can travel to the second light bulb and back, third light bulb and back, or fourth light bulb and back. But this time, if the second one goes out, it can still go through the first one and get back. It can still go through the third one and go back, or it can go all the way down to the fourth one and get back. So the other three light bulbs in this case are going to stay lit. They're not going to turn off. So in a parallel circuit, when one goes out, it's just localized. So a lot of times our houses have parallel circuits. When one of your, let's say lights in your kitchen goes out, it's not all the lights in your kitchen that go out. It's just that one light bulb. So you can just replace that one. So that's because they are on a parallel circuit, multiple pathways. Drawings of electrical diagrams are going to look different, but they all kind of have the same components. And we're going to be seeing these so we can diagnose what's a series, what's a parallel. So it's important to understand this stuff. And guys, if you want to go into a trade school, make a lot of money, we are in grave need of electricians. That's one of the populations is getting older and older. So we need more people to come into that field and replace them so that they can retire. And we still have people that know how to do this. But they use these drawings a lot to help them diagram and figure out where their circuits are going to go and how they're going to work. Wires are often drawn with lines. If there's a switch, there's a break here. So this is when it's open, that's when the lights are off. When it's closed, that connects the circuit, the lights turn on. You may not want all the electricity to go to an object, so you might have resistors in there. That's going to either slow, that's usually going to slow the electrons down. There's a less current, things like that. Single cell or multi-cell batteries are going to look like big lines and little line dashes vertically, and then light bulbs are little loop-de-loops in there. So here we can see the series circuit. Here's the negative side of the battery, comes through the first light bulb, second light bulb, third light bulb, and back. So obviously if one of these goes out, the whole pathway is broken and it stops. Here we can see that same example of a parallel, can go through the first, second, or third. So if one of these light bulb goes out, it's just that one that goes out. Now, there are other things that we need to understand about the differences between series and parallel. As you add more light bulbs to a series circuit, the lights get dimmer and dimmer and dimmer. Now, why is this? Well, remember, energy is never created or destroyed. So how does a light bulb actually work? Well, the electrons are speeding around this circuit, and as they go through the light bulb, they pass through a metal that doesn't allow them to flow as easily. That slows them down. But remember, that energy has to go somewhere. So as you slow those electrons down, that energy, that kinetic energy, gets turned into light or heat, and then that heat, eventually starts to cause the metal to glow and produce light. Sorry, I should talk about each one there. So it produces the heat, and then the heat builds up, and the metal starts to glow, and that's what gives off the light, if it's a normal light bulb. If it's a LED, or if it's using some kind of gas, it's a similar idea. You're sending that electricity through the gas. It's heating the gas, and the gas is beginning to glow and give off light. But the key here is in a series circuit, think of these as a little hill, because remember, each one is a resistor. Each one slows it down a little bit. So in this case, you only have one hill on your run. Okay, you can probably go through that at your normal speed. Well, if you take a route that causes you to go over 2 hills while you're running, well, that's going to take more energy away. So there's going to be less energy for these light bulbs. It's going to be a little bit dimmer. If you go through over 3 hills on a run, you're going to use lots and lots of energy. So there's less going through each one. So as you add more loads to a series circuit, each one gets less energy, because all the electrons have to go through each one before getting to the next. This is not true of a parallel circuit, because if we go back and we take a look at a parallel circuit, you get the fresh electrons directly from the energy source each time. The electrons don't have to go through each one. In fact, they can't. Once they turn down this pathway, they have to continue in that same direction. They're going to go back to the starting point being drawn by that positive charge. So it's not like they're going to go through one and be like, I think I'm going to take a right and go down. No, it doesn't work that way. So they're going to take the path that gets them back to the positive charge the fastest. So boom, boom, or boom. But each time the electrons only go through one light bulb. So I could put 1,000 light bulbs on this string. They're never going to get dimmer. All right, so obviously we've been talking a little bit about things that allow electricity to flow easily, aka conductors, and things that do not allow the electricity to flow easily, which we call insulators. So we have conductors and we have insulators, and we often use them together. So conductors, you guys would have come up with some of these answers very easily. Metal is a conductor, right? Copper is very good. Aluminum is pretty good, but most metals give away electrons, and that is the key. That's why we're talking about electricity when we're talking about the atom and we're talking about elements. Remember, metals are on the left side of the periodic table. When we were talking about ionic bonds, what did those metals like to do? They like to get rid of electrons, right? Because they have 1 or 2 or maybe 3 electrons in their outer shell. So they don't want to take in electrons, they want to give them up. So that's why it's really easy for metals to be conductors, because if you give it an extra electron, it's like, I don't want this thing, let me pass it on to the next guy. And so that just happens again, again, and again. And that's how the electricity jumps. The electrons jump from one atom to the next. If we take a look at insulators, insulators are things like styrofoam, rubber, plastic, and paper. Think about those little toys. If you have kids, you go to McDonald's and there's a little tab in there that you have to pull out, and then the toy makes some kind of sound, or the battery's engaged. That's because that paper or plastic tab in there is in between the battery and the connector for the circuit, and that way the battery doesn't die before your kid gets the toy and has a meltdown in the back seat of the car, right? So in this case, the insulator is there so the battery stays fresh. Then when you pull that tab out, it connects the circuit and the electrons begin to flow. So insulators are often things that include, nonmetals. And why do nonmetals are not good conductors of electricity? Well, remember, those nonmetals are looking to take in electrons. They're not looking to give up electrons. So that's why they're not very good conductors of electricity. All right, so I talked a little bit about resistance, right? What is resistance? Because this is a big thing when you're talking about electrical circuits. Every circuit has resistance and it has to be taken into account because resistance is the opposition to the flow of electrical current. And remember, if you're going to slow the electrons down, that energy has to go somewhere and it comes out as heat. So if you've got a really good wire, a really good conductive wire, it's going to have a low resistance. But if you have a really bad wire, it's going to have a bigger resistance. And the bigger the resistance, the less current that gets through. Now, sometimes you want that. Like I said, with your phone, you don't want your phone to get, the full juice of electricity from the grid. That would fry your phone so it would no longer work. So you don't put, a great wire in there. You put something that slows it down a little bit. You might even have a resistor on there. That's why you don't just have a cord. You have that little block. That block in there is going to change the amount of electricity coming from the wall outlet to your phone. So it's very important that that's there. So good conductors have a very low resistance. They still have some. No wire is perfect. So, all wires are going to slow electrons down a little bit. But the key here is there are things that we can do intentionally to make sure we either have a really good conductor with low resistance or maybe a less good conductor with a higher resistance. This is something measured in ohms, okay? I'm going to butcher this trying to write it on the screen, but the symbol for ohms looks like a little upside down horseshoe. It's not so bad, but that's what the ohm symbol looks like, okay? You'll see that a lot in this lesson as we go through the practice and whatnot. Okay, so what kinds of things affect a wire's resistance? Well, the first is the material. We talked about that. Aluminum, copper have a pretty low resistance. Thickness matters. If you look at the cord that goes to your fridge or microwave, and then you look at the cord that goes to your phone, there's an obvious difference in thickness. Why is that? Well, because your fridge or microwave is going to require a lot more electricity than the phone. So the thicker the wire, the lower the resistance. Obviously, there's more metal in there. That creates an easier path for the electrons to flow. Length matters, okay? Shorter is actually better, okay? The shorter the wire, the lower the resistance. I hear people all the time going, well, why can't I have like a 10-foot phone cable or a phone charger, right? Why does it have to be so short? Why am I stuck to this outlet? Why am I tethered to the wall? Well, the reason for that is because the longer the wire, the more resistance that builds up over the length of the wire. So the things that need a lot of electricity are not going to have a very long wire because that's just going to increase the resistance and increase the heat that wire is going to put out. Think about your microwave. If you have a microwave, that cord is incredibly short. The reason for that is because microwaves use a lot of electricity in a very short amount of time. So you need low resistance there. And then if you're dealing with electrical circuits, you can also cool them. The colder it is, the lower resistance it has. Think about computers. Computers have fans in them. The reason for that is to take away the heat from the computer, and that allows electricity to flow through there a little bit easier. So some people will like super cool their processors or something like that. And that just means that it can do more computations per minute because it has less electrical resistance. So if you wanted a perfect wire, you'd probably make it out of copper, be very thick, very short, and if you can, figure out a way to cool that wire. It's going to make it flow just that much easier. So we talked about current, but another thing that we can measure is how many volts something has. Volt is the measure of energy given to the charge flowing in a circuit. So the greater the voltage, the greater the force or pressure. I want you to think of like a garden hose versus a fireman hose, right? Obviously they're different thicknesses and everything, but just think about how hard the water is pushed out. When you have a garden hose, it's just kind of slowly coming out there. It may go like a foot in front of you, a foot or two in front of you. But unless you kind of, put your thumb in there to spray it a little bit further, or if you have, one of those attachments you could put on the end to shoot it out and jet spray it. It's not going to have a very high pressure. But a fireman hose, man, those things have to be able to shoot water out across a great distance. So they have a much, much higher force pushing the water through that hose. That pressure is going to be higher. So the fireman hose, if we're talking about it as electrical, the fireman hose has a much higher voltage than the garden hose because it's putting out the water at a much, much faster rate. So voltage is how quickly or how hard, how much force there is pushing the electrons through that circuit. So remember, now we have two measures. We have amps, okay, and we have volts. So amps is the current and volts is the pressure. So a good example, again, is thinking about the hose. The amps measures how much water comes out of the hose. Is it a gallon? Is it 10 gallons? Is it 100 gallons? That's how much current is flowing, how much electricity actually gets through the circuit. But volts measures how quickly that happens. Right, so maybe you have something with a very low amount of amps. You're not getting a lot of electricity through, but it has a high voltage. It's happening very quickly, short burst of energy. Or maybe you want the opposite. Maybe you don't need a lot of pressure, or excuse me, a lot of electricity, but and you don't want it to come very quickly. Well, then you're going to have a low amount of amps and a low voltage, right? So that would have the more gentle stream of electrons for more delicate equipment and things like that. So amps, how much? Volts, how fast? So this brings us to Ohm's law, because if we know how much less electricity gets through and how much force it's being pushed through with, we can find out how much resistance that wire has. So we simply take the voltage divided by the current, so volts divided by amps. You will see me write this, and bear with me here. I'm going to try and do it well. But when I write Ohm's law, you'll see me write this. Ohm's equals V. Oops, that's a V. There we go. V over A. Okay. And this is how I will write it. And for units on this one, the unit for ohms is this symbol, amps is A, volts is V. Or you can just write amps or volts after that if you want. All right, so let's put this into practice. If we have 100 volts and 25 amps, how many ohms? Remember, the equation is ohms equals volts divided by amps. So if I have 100 volts and 25 amps, how many ohms of resistance are there? There are 4, because 100 divided by 25 is 4. If I have 150 volts, but only 10 amps of electricity are making it through, what is my resistance of this wire? Well, 150 divided by 10 gives us 15 ohms. So let's look at these top two. Here I have a good amount of energy coming through, and a good amount of energy coming through and a slower rate than this one, right? So there's a very little amount of resistance here. But in this case, I had a higher pressure, but less electricity making it through. How do I know this? Well, the only way that's true is if the resistance is much higher, okay? So just try and pay attention to what these numbers mean and think about volts is pressure, amps is the amount. If I've got 30 volts coming through, or 30 volts pushing my electrons through, and only 15 amps of current making it through that circuit, well, 30 divided by 15, this is a low resistance wire. It only has 2 ohms of resistance. Hey, can you not come in here and mess things up, please? Thank you. All right. Now, just like with any formula, if I have 2 out of 3 of variables, I can always solve for the last one. So in this case, I know how many amps I have, but I know what the resistance is. I need to know what the pressure is. What's the voltage here? So if I have the amps is 5, the ohms is 9. How do I undo division? Because I gotta get V by itself. If I undo division, well, I'm gonna multiply both sides by that number. So I'm gonna multiply both sides by 5. So 5 times 9 gives me a voltage of 45. And if I know the volts and the ohms or resistance, I can obviously find the current. This one is a 2-stepper. So what I'm gonna have to do is I'm gonna have to multiply A to both sides first. So I'll have 6A, let me diagram this one out so I'm not just talking through and confusing people. So we have 6 ohms equal, come on. Oh, not gonna let me draw all over there? Cool, all right. I got space over here. We got 6 ohms and we know the voltage is 48 and we don't know the amps, okay? So what we're going to do is we're really just going to switch these two by multiplying by A and then dividing by 6. So it's really going to get 48 divided by 6, which gives us an answer of 8 amps. There's 8 amps of current coming through that wire. All right, so how can we use electricity and how is electricity and magnetism related? Well, remember, electricity is the flow of a negative charge. So that can obviously cause charges to build up in something. So in an electromagnet, that is a magnet made from electricity. So what we can do is we can coil a wire wrapped around iron or steel, and then you run electricity through that. And the negative charges of the electricity cause the charges in the iron to align, making it magnetized. So again, if we have a piece of iron or steel, we take a coil and we wrap it around. Oh, that's weird, I don't know why that did that. But in any case, it wraps around those electrical currents, those electrons, I don't know why it's doing that, it's annoying, are gonna travel through that, and that's gonna cause one side to become positive and one side to become negative, okay? Charging that. Now we use electromagnets in all kinds of places. You know, if you've ever seen like a junkyard, those big cranes, right? They got a big circular thing here. Well, that circle piece is a bunch of coiled wire in there around a giant core of iron. So what happens is the guy in the little box flips a switch that sends the electrical current to run through the wire, charges up this, and then you can pick up the car or whatever junk, metal junk you're trying to move with that. Okay. We can also use electromagnets a lot for safety features. If you've ever, I don't think our school does, but some schools have, you know, those doors that are held open by magnets. Well, they're electromagnets. The reason for that is in the event of a fire, a lot of times electricity, the circuits get broken, so the electricity goes out. Well, what happens if the electricity goes out? Well, it's going to lose its charge, and then it's not going to be magnetized anymore. It's going to drop whatever it's holding if it's the crane, but in the case of the door, it's going to allow the door to close. And in the event of a fire, a closed door is going to help it contain the fire. It's not going to allow it to spread as easily. So it's really an ingenious design to have those electromagnets there. Then the power goes out and all the doors automatically shut without someone having to run through and shut them all. So electromagnets, sending electricity through a coil to charge up a piece of iron or steel. All right, we can actually use motion to generate electricity. That's called a generator. So a generator is a machine that changes mechanical energy into electrical energy. So in this case, we're going to use the opposite. We're going to have a magnet. I guess I'll draw this vertically again. We're going to have a magnet, but this time it's going to be one of those permanent magnets, not one of those temporary magnets. And what we're going to do is we're going to attach it to something, some kind of motor or device that's going to cause it. This is my motor, say motor, okay? It's going to cause this magnet to move back and forth. And we move it back and forth around that coil of wire, right? And that movement of the magnet is going to cause the electrons in that wire to be pulled as the charges of the magnet move. That's going to cause them to move back and forth, generating an alternating current, which is electricity. If you've ever seen one of those mechanical flashlights, you know, one that you can wind up or one that you shake, it's working the same way. It's got a magnet in there, you're shaking it, it's moving it back and forth. That's causing electrons in the coil wire around that magnet to move and then generate electricity for you to use the flashlight or whatever. Or if the power goes out, you know, a lot of people or a lot of schools and hospitals have a gas generator. So if you're in a hospital and the power goes out, you can't just be like, hey, we're in the middle of surgery, I guess we're gonna take a break. No, you need that electricity. So what happens is backup generators kick on, they burn gas to run a motor, moves magnets, generates electricity, okay? All right, and then we can do the opposite. We can use electricity to make mechanical things happen or do work. That's what a motor is. So it's a device that changes electrical energy into mechanical energy. So, you turn on a blender or a coffee grinder or something that's using I don't know. It's taking that electricity and then doing the reverse, causing the motor to move, and therefore it does the job that it's supposed to do. And guys, that's really it for electricity and magnetism. So all that you guys really have left for today is two things. And let me go ahead and share that screen back to Google Classroom. So you guys have the Ohm's Law worksheet. This is very, very, very simple. All you're doing is using Ohm's Law to solve for one of the variables. So this first one, they give you the volts and the ohms, and they want the amps. And then down here, they give you the amps and the ohms, and they want the volts. And then on the back, they give you the volts and the amps, and they want the resistance. Okay, it's going to give you a couple that are going to look for a pattern. So like in this one, they keep the resistance the same, in these three rather, 2, 3, and 4, they keep the voltage the same, but they change the resistance. They're going to ask you, how does that affect the current, right? Down in the next one, there's a couple 3 where they keep the amps the same, but change the resistance. How's that going to affect the voltage? So not only is there a little bit of math in here, but there is some concept understanding as well, which I think is really good. So you guys will finish this. It looks long, it's 70 questions, but they go very quickly because it's a simple formula. And then all that you have after that is the X ticket. So just hop on here, fill out that X ticket and get that back to me. Just a look ahead, guys. Monday, we have the last bit of new information or new material. That's going to be on fusion and fission, some things that generate energy and electricity. So we're going to take a look at that. That's only going to be half the lesson. The second half of Monday, we're going to begin to review for the final. Tuesday, we're probably going to finish up that review. It won't take very long. We may just get through it all on Monday. I haven't decided yet. We'll see how much time we have. But Wednesday, I'll send it Tuesday. So you can either take it Tuesday or Wednesday. The final exam will be available, but you have to take it quickly so that I can grade it and get it in the grade book before grades close. So we are kind of towards the end of the term. So it is very, very important that you're finishing things up, getting it turned in, and making sure it grades where it needs to be before the end of the term. Okay. Well, thank you for zooming in today, guys, and I will see you on Monday when we start to finish up material and review for the final. All right, guys, have a good day.